All right, today we will prove and consider consequences of a result called the triangle inequality. Now, in this chapter, we will prove a number of results that involve inequalities and triangles, but one of these gets to be called the triangle inequality. It's really extraordinarily important and powerful. You'll see later on that it gets applied in situations where it comes as a real surprise, but historically, this one is called the triangle inequality. And here's how I'd like to introduce it. So let's say that we have 2 points. Here they are, A and B. And what we'd like to consider is 2 ways to get from A to B. One way simply goes, as it were, directly from A to B, that is along the line segment AB. And the other goes up to a point C, that is along a line segment AC, and then comes back to B from C. That is, we have the path directly from A to B, and then the path from A up to C, and then down to B. And my question is this: which of these paths is shorter? The direct path AB, or the broken path, you might call it, ACB? Now the answer, of course, is obvious, right? It does not mean that this will be difficult. The answer to this is obvious. Obviously, AB is shorter. And then the question becomes, like, what really have we said? Because we ended up with a triangle, right? We talked about paths initially, but of course, then what we have is a triangle. What we really said is this, is that the length of any one side of a triangle is greater than the sum of the lengths of the other two. So for instance, we may say in this case, just to write down all 3 truths of this form that we have for this particular triangle, ABC, we may say that AC, of course, plus BC is greater than AB. And for each side, we're going to have a sum greater than it. So there's going to be an AC over here, there's going to be a BC over here, and the sum of the other 2 sides is greater than it. So this will be AB and BC. And then finally for BC, this will be AB and AC. Hopefully I got all that right. But what this says is that the sum of any 2 sides is greater than the third side. And this is the triangle inequality, okay? That theorem about triangles and inequalities that has the status of the triangle inequality. This is what it says, okay? The sum of any 2 sides of a triangle is greater than the third side. Now, so we accept this, right? We believe that this is true, but you know the drill, right? We don't get to say just that. We have to give its position in the system that we wish to build. And the way that we do that is we say that it's a definition, a postulate, or a theorem. And if it's a definition or a postulate, it's like in the foundations of the system. It doesn't get derived from anything. If it's a theorem, it's not like in the foundation. It gets derived, it gets proven. Well, it's certainly not a definition. There's not anything like the definition of triangle, which is just 3-sided polygon or greater than, which tells us that this must be true. If I were to call it a postulate, I don't think that anybody would complain at all, unless you had a deep prior knowledge of Euclidean geometry, which you probably don't. I've said before that postulates are our basic assumptions that should appear obviously true, and this one certainly does. But we don't need to call it a postulate, okay? As I think I've mentioned before, if we're able to prove a statement is true, it seems to me like good policy to actually give the proof, okay? To actually give the proof. Oh, and I might mention something here. There are a number of contexts in this class in which the word spelled ASS comes up. That's always a source of fun in the class. We've seen ASS congruence, which we know has counterexamples, so we do not use that in our congruence proofs. We've also seen the bridge of asses. That is Euclid's proof of the isosceles triangle theorem. Here's another example of how it is, or where it is that we can use the word spelled ASS. Okay, that is ass, if you like. Okay, so Euclid, we follow Euclid here. We will prove the triangle inequality. And some mathematicians after Euclid complained about this, because when you see the proof is not particularly difficult, but it's also not the easiest proof that we do, and it's far from obvious initially anyway how it would be proven. I mean, I'll guide you through it, and I don't think you'll find it too hard. But if I were to just throw you into it and say prove this, you might stumble. You might not know how to do it. Okay, so the proof is not the easiest, and then the proof itself is not as obvious as it were as the statement that gets proven. And some mathematicians haven't liked this. They didn't like that a statement that in itself is quite obviously true receives a non-obvious proof. And I honestly kind of get that. I feel that. But still, it seems to me, and the reason why we can bring up ASS here is that this complaint was often put in this form, is that even the ass knows that the path that it should take to the bale of hay, let's say our ass is hungry, is the direct path, right? Is the line segment path, right? And not that broken path. Even the ass knows that it's true. That's how obvious that it is. And like I said, I get that. I sort of feel that objection. But nonetheless, it seems to me that since we're able to prove this, we should prove it. And I'll guide, I'm not going to talk through the proof here, but I'll guide you through the proof on the worksheet so you can see it there. And let me mention as well that the proof is Euclid's proof, okay? This is like sort of a modern recreation of Euclid's proof. Euclid is the master, we follow him here. Now, what this gives rise to is the so-called triangle test, okay? Which, for what it's worth, I've seen this come up on standardized tests before. It's the essay creators of the SAT like to use it, for instance. So let us say that we're given three positive quantities A, B, and C, and we wish to know whether it could be that there exists a triangle with sides of length A and B and C. Well, it must be that the sum of any two is greater than the third. Okay, and if that's true, then it could be a triangle, and if it's not true, it cannot be a triangle. So that's how one applies the triangle inequality to test whether three given side lengths could be side lengths of a triangle. And there's a way to simplify this. So if you're given three side lengths ABC, order them from least to greatest. And if the sum of the first two, which are the smaller, is greater than the third, which is the largest, then of course the sum of any two will be greater than the third. So that's like the simple way to apply the triangle test that comes from the triangle inequality. Take your side lengths, order them from least to greatest. And then if the sum of the first two is greater than the third, you can have a triangle, otherwise you cannot. So a very simple example. Could a triangle have side lengths of 8, 3, and 5? Well, it should be fairly obvious just immediately, but let's say we do what we did. So order them from least to greatest, so that'll be 3, 5, 8. Then ask whether the sum of the first two is greater than the third, not just merely equal to or greater than, but strictly greater than. And the answer is no. Okay, 3 plus 5 equals 8. It's not greater than 8, so there can be no triangle. And if one were to ask, well, let's say if we tried to make a triangle with side lengths of 3 and 5 and 8, so like we have our side length of 8, and we wanted to anchor at one end a side length of 3, and at the other end a side length of 5, of course what they're going to do is they're going to meet at a point on the 8, right? So if one were to attempt to make a triangle with sides of 3 and 5 and 8, one would fail. The best that one could get is simply a line segment. All right, so here's another example. 12, 18, 8. Can there be a triangle with these side lengths? Again, my suggestion is this, is order them from least to greatest. So 8, 12, 18. Ask whether the first two, the 8 and the 12, whether their sum is greater than the third, and it is. 20 is greater than 18. So yes, check. This absolutely can be a triangle. Now, here's a nice little application of this. Let's say that we have a triangle that has two sides that measure 5 and 17. What's the range of possible values for the third side? Okay, like, I don't know, a million. I mean, obviously a million couldn't be the side length, the third side length. But it seems to me fairly obvious that 17 could be, because it would be isosceles in that case, and that would be possible, right? So what's the range of possible values? Is there a way to put this? Well, let me show you how to approach this. So let S represent the length of the third side, okay? And then we can write three equations, okay? And here are the three equations that we can write, and we're going to work with those. So we know that S plus 5 must be greater than 17. The sum of two sides is greater than the third. We also know that S plus 17 must be greater than 5. And we also know that 5 plus 17 must be greater than S. Okay, that's just like the three ways that the triangle inequality applies to this triangle. And then let's work with these. Okay, so take the first one. It follows that S must be greater than 12. If we subtract 5 from both sides, I assume you can do just a little basic algebra here. So subtract 17 in the second one. So S must be greater than negative 12, I think. And then how about I turn the other one around so that I have S on the left-hand side. So S less than 22. And then let's think about these, okay? So let's think in particular about the first two of these, which both say what S must be greater than. S must be greater than 12 and S must be greater than negative 12. Now, one of these is redundant, okay? They both must be true, right? This is not like a choice. It's not pick one that's true. They're all true, okay? And if they're all true, of the first two, one of them is redundant. That is, one of them, if true, guarantees that the other is also true. And of course it is S is greater than 12. If S is greater than 12, then it's guaranteed that S is also greater than negative 12. So that S greater than negative 12 doesn't convey any additional information that we did not already have. So the two inequalities that convey information that we need to use is S is greater than 12 and S is less than 22. And we can write this into a nice little compound inequality that S must be greater than 12 and S must be less than 22. Okay, so any of those values would be fine. Oh, and a little side comment here. I don't know why, but sometimes students have a prejudice in favor of integers. That is, they'll think that, oh, side lengths are 5 and 17, so the third side's going to be an integer 2. I never said this. Okay, so don't think that. This is our quantities here are all real numbers. So any value less than 22 would be fine. So like 21.999999999, however many nines you want, so long as it's not infinite. That would be perfectly acceptable. And any value greater than 12 would be acceptable. So like 12.00000, however many zeros you want, and then a 1, that's perfectly acceptable as well. Okay, so anything in that range. Now, let's generalize this, okay? So let's say that we have two given side lengths A and B. Okay, those are like just stand-ins. They represent particular values. And then we wish to find out the range of possible values for the third side S in terms of A and B. Well, we can do the kind of work that we did before. So the sum of any two sides must be greater than the third, so A plus B must be greater than S. And A plus S must be greater than B. And A plus, oops, let me get this right. So A plus B must be greater than S. A plus S must be greater than B, and I'll get it. And the third one must be greater than A, so B plus S must be greater than A. Yeah, so those are the three inequalities that we have to have. And then let's solve each of these for S, right? It would be nice to have S on the left side, so I'll say that the first one simply will be S is less than A plus B. And then for the second one, if we subtract A from both sides, we wish to solve for S, or isolate S on one side, we'll get S is less than B minus A. And then for the final one, if we subtract B from both sides, we'll get S is greater than A minus B. All right, so we definitely need the first of these inequalities. That provides like the upper bound. S must be greater than A plus B. But let's consider the other two, which will provide the lower bound somehow. That is, tell us what S must be greater than. Well, think about the relationship of A minus B and B minus A. Think in general about the difference between A minus B and B minus A. Let me do a little work off here to the side, okay? So if I were to have A minus B, and let us say that I factor out a negative 1, which I can absolutely do, and then what do I get, right? Well, if I factor out a negative 1 from A, I get negative A, and if I factor out a negative 1 from B, I get positive B, which I can rewrite this as negative 1 times B minus A. And you could distribute the negative 1 through and convince yourself that this is correct if you like. But what this really shows is that the difference between A minus B and B minus A is the sign, okay? One is negative and one is positive. Okay, and then like before, the one of these that is negative, we can dispense, because the one of these that is positive will guarantee that the one that is negative must also be true, right? But then we have an issue, okay? Because though B and A represent particular quantities, we don't know what those are, right? So we don't know which of B minus A and A minus B is the positive one. So let me ask you a question. Are you familiar with a mathematical function that, whether it's given A minus B or B minus A, will guarantee that it returns the positive of those two values, A minus B and B minus A? That's the absolute value function, right? So we can replace both of these with the requirement that S must be greater than the absolute value of A minus B. Or you could write equivalently that S must be greater than the absolute value of B minus A, because the absolute value of A minus B and the absolute value of B minus A are the same quantity, okay? And then if we put it all together, I'll just show you, here's the inequality that we get. If A and B represent two side lengths of a triangle and S possible values for the third side, then S must be less than A plus B, and it must be greater than the absolute value of A minus B. And that is a really nice little result.